Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
If you imagine looking up at the night sky right now, you see the moon and you usually just think of it as this silent, dead rock orbiting our planet.
Right, or maybe like a stepping stone for space exploration, but basically just a rock.
Exactly, just a rock. But what if its true value is actually as the largest, most ambitious scientific instrument humanity has ever used?
It is a massive paradigm shift. I mean, it completely changes how we look at celestial bodies.
Because we are going to talk about how the moon's rugged, cratered surface and its really uneven crust might actually be the exact key we need to hear the most elusive whispers of the universe, which are gravitational waves.
Yes, and we are talking about turning an entire natural satellite into a piece of diagnostic equipment.
It's just wild to me. The scale of this idea is sheer wonder. We're turning a celestial body into a tool.
It sounds like science fiction, I know. But I promise, the incredibly precise, multidisciplinary science that makes this wild idea possible is very real. It's grounded in hard physics.
And the best part is, for you listening, if you've ever felt like your own imperfections or your rough edges hold you back, well, you're about to find out how the moon's actual physical flaws are its greatest scientific superpower.
That is exactly the heart of this. The flaws are the feature, not the bug.
Right. So, before we can understand how the moon listens, we really have to understand what it's listening for, right? So let's talk about gravitational waves.
Definitely. It is the crucial first step.
Because to a lot of people, ripples in the fabric of space-time sounds like a line from a movie to explain why the warp drive is broken.
Yeah, the sci-fi comparison happens a lot. And honestly, it's because the reality of general relativity is just wildly counterintuitive to how we live our lives.
Because we just think of space as empty.
Right, we are totally conditioned to think of space as an empty room, just a static three-dimensional void where things happen.
Like a stage.
Exactly. But Einstein showed us that space-time is a dynamic, flexible medium. It has a geometric elasticity to it.
Okay, elasticity, meaning it can stretch.
Right. When something with mass accelerates, it distorts that medium. So if you take unbelievably massive objects like two black holes or incredibly dense neutron stars.
And these are huge.
Oh, massive. And when they spiral toward each other and eventually violently collide, they displace that space-time medium so aggressively that the distortion travels outward.
Okay, so kind of like dropping a bowling ball into a swimming pool. The water has to go somewhere, so it pushes outward in a wave.
That's a helpful visualization, sure. But there is a really critical distinction in the mechanics there.
Oh, really? What's the difference?
Well, a water wave is an acoustic or mechanical wave traveling through a medium.
Right.
The water is moving.
Right.
But a gravitational wave is a fluctuation of the medium itself. It's the space-time that is rippling.
So the pool itself is waving, not the water.
Exactly. So when a gravitational wave passes through you, it is literally stretching and squeezing the physical distance between the atoms in your body.
Wait, stretching the distance between my atoms.
Yes. It stretches space in one direction while simultaneously compressing it in the perpendicular direction. We call this a quadrupole moment.
A quadrupole moment. Okay, so the actual fabric of reality is warping, which means every object sitting in that space, like the Earth, a building, my actual body, is briefly getting distorted.
That is exactly what is happening.
But, obviously, I don't feel myself getting stretched and squeezed like a funhouse mirror when a black hole merges a billion light years away.
No, you don't. And you don't feel it because the distortion is infinitesimally small by the time it reaches us.
How small are we talking?
We're talking about a change in distance on the scale of a fraction of the width of a single proton.
Oh, wow. A fraction of a proton. That is unimaginably tiny.
It is. Which is why we had to build the most sensitive machines in human history just to prove these waves even existed in the first place.
Right. Machines like LIGO, the Laser Interferometer Gravitational Wave Observatory. I know those are massive facilities.
They are incredible feats of engineering.
They're basically these L-shaped vacuum tubes extending for miles out in the desert, right? Bouncing lasers back and forth just to measure that microscopic stretching.
Right. LIGO is an absolute triumph. It uses optical interferometry to measure those changes with mind-bending precision.
But they have a limitation, don't they?
A massive limitation. And this is the fundamental problem that Earth-based observatories face. Gravitational waves are not just one uniform thing.
Like how light has a spectrum, radio waves, gamma rays, all that.
Exactly like that. Just like light has a spectrum, or sound has a spectrum of low and high pitches, gravitational waves operate across a really vast spectrum of frequencies.
Okay.
And our Earth-based detectors are just utterly blind to a massive portion of that spectrum.
Blind in what way, though? Because if the machine can detect a change smaller than a proton, shouldn't it be able to catch any wave that causes that change?
You would certainly think so, but it actually comes down to the frequency of the wave.
The frequency. So how much time passes between the peaks of the ripple?
Exactly. LIGO is highly tuned to hear high-frequency gravitational waves. So roughly between 10 hertz and a few thousand hertz.
Okay, and what makes those high-frequency waves?
These are the frantic, rapid-fire waves that get produced in the final fractions of a second when two stellar mass black holes merge.
So LIGO is really just listening to the cosmic grand finale. It's catching the explosive crash at the end of the song.
That's a great way to put it, yes. But long before those black holes actually touch, they spend millions of years spiraling around each other.
Just orbiting and orbiting.
Right. And as they get closer, they emit lower frequency gravitational waves.
Okay.
Specifically, there's an entire class of cosmic phenomena, like the inspiral of intermediate mass black holes or binary white dwarf systems, that emit waves in the 0.01 to 1 hertz frequency range.
0.01 to 1 hertz.
Yes, we call this the dci-hertz band.
Okay, the dci-hertz band. So we essentially have a missing octave here.
We do, a huge one.
It's like we are sitting in the front row of the world's greatest symphony, and we can clearly hear the violins shrieking away during the climax, but we're wearing earplugs that block out all the cellos and the baritones building up the tension beforehand.
That analogy is spot on. We know these massive things, these intermediate mass black holes, are out there dancing around each other, but we are completely deaf to the music they make while they do it.
So we're missing a crucial part of the symphony. But if this decihertz band is so crucial, and we already know how to build a machine like LIGO, I guess I just don't see why we can't just build a bigger one.
A bigger LIGO?
Yeah, why can't we just build a better, heavier detector here on Earth and specifically tune it to catch this 0.01 to 1 hertz range?
It's a logical question, but the short answer is that the Earth simply will not allow it.
Won't allow it.
Right. Our planet is simply too noisy for low-frequency observation.
Okay, when you say noisy, I assume you don't just mean like traffic and construction noise outside the lab.
No. The problem is planetary. Earth is a geologically and atmospherically hyperactive world.
Oh, right, because it's a living planet.
Exactly. The oceans are constantly crashing against the continental shelves, and that creates this continuous low-frequency hum.
I never even thought about the oceans making ground noise.
Oh, they do. And deep beneath us, tectonic plates are constantly grinding together. We have microseismic activity happening globally all the time.
But wait, isn't LIGO already isolated from that? Because I've seen the diagrams. They hang those mirrors on these incredibly elaborate pendulums and shock absorbers just to block out the vibrations of the ground.
They do, and those seismic isolation systems are brilliant. But they are really only effective at blocking high-frequency jitters.
Oh, so they can't block the slow stuff.
Right. You cannot mechanically isolate an earthbound instrument from the low, slow, rolling vibrations of the deci-hertz range. The wavelength of the seismic noise of the Earth perfectly overlaps with the gravitational waves we are trying to hear.
Okay, so the Earth is naturally vibrating at the exact same pitch as the black holes.
Exactly. But it actually goes even deeper than the ground shaking.
Deeper how?
Well, let's say you could magically float a detector so it never touched the ground at all, completely isolated.
Okay, that sounds ideal.
It would be, except you still have to deal with Newtonian gravity gradient noise.
Gravity gradient noise. Okay, that sounds like a very serious physics hurdle. What is that?
Think about our atmosphere for a second. When a massive weather front rolls over an observatory, or frankly, simply when a large, dense cloud moves overhead.
A cloud?
Yes, a cloud. The localized mass of that air literally changes the gravitational pull in that specific area.
Wait, seriously?
Yes. A moving cloud exerts a tiny fluctuating gravitational tug on the actual mirrors of the laser detector.
You've got to be kidding me. A passing cloud can pull on a laser mirror enough to ruin a measurement of a black hole.
Absolutely. When you are measuring distances at the subproton level, mass is mass. Changes in atmosphere's pressure, variations in groundwater, the pull of the tides, all of these things continuously shift the localized gravity field on Earth.
Oh, wow. So the Earth's gravity isn't even completely static.
Exactly. And at that 0.1 hertz level, this Newtonian noise creates a fundamental wall.
A wall that you just can't build around.
Right. No matter how advanced your technology gets, the Earth's own shifting mass just drowns out the signal. You fundamentally cannot build your way out of it on a living planet.
That makes a lot of sense, actually. The venue is just too chaotic. It's like we're trying to record a whisper in the middle of a bustling factory floor.
It's impossible.
But if Earth is completely disqualified, why is the immediate leap to use the moon itself as the detector? I mean, I know there are plans to put laser interferometers in space, right?
Space-based interferometers.
Like where they just fly satellites millions of miles apart. Why drag a massive dusty rock into the equation at all?
So space-based interferometers are absolutely part of the future, but they're incredibly complex, they are vastly expensive, and they face their own hurdles with things like spacecraft drift and solar radiation pressure.
Right, space is hard.
Very hard. But using the moon offers a completely different, complementary method of detection, and it's based on a much older concept in physics.
Older, like pre-LIGO.
Yes. It brings us back to a technology called the Weber bar.
The Weber bar. Okay, I've actually seen historical photos of these things.
Oh, you have?
Yeah, they look like giant, solid metal water heaters hooked up to a bunch of wires in a lab. But how does a big metal cylinder detect a ripple in space-time?
So it relies on acoustic resonance. Joseph Weber pioneered this idea back in the 1960s.
The 60s? Wow.
Yes. His theory was that you didn't need to bounce lasers over miles of vacuum. Instead, if you take a massive, solid object like a very large cylinder of aluminum and a gravitational wave passes through it.
It interacts with the metal.
Right. The stretching and squeezing of space-time will interact with the atomic structure of the metal itself.
Okay, this is that quadrupole effect you mentioned earlier.
Exactly. It stretches the cylinder one way and squeezes it the other.
Okay.
And if the frequency of that gravitational wave matches the natural resonant frequency of the aluminum cylinder, the wave actually deposits a tiny amount of acoustic energy into the metal.
Which means it makes sound.
Well, the solid object literally begins to ring.
Oh, wow. It rings internally.
Yes, it vibrates, almost like a bell being struck by the fabric of reality itself. And Weber surrounded these metal cylinders with highly sensitive piezoelectric sensors just to try and detect that microscopic ringing.
That is such a cool concept. But Weber's bars didn't ultimately discover gravitational waves, right? Because LIGO did.
Correct. LIGO made the first confirmed detection.
So if LIGO won, why are we dusting off a 1960s concept now?
Because Weber's bars were fundamentally limited by their mass.
They just weren't big enough.
Exactly. An aluminum cylinder in a laboratory is simply not massive enough to capture enough energy from a wave to stand out clearly against the thermal noise of the metal's own atoms vibrating.
Okay, the metal itself is too jittery.
Right. To make a resonant mass detector truly effective, you need an object with an astronomically large mass.
Oh, wow. Okay, I see where this is going.
Do you?
Yeah. So instead of a 2-ton aluminum cylinder in a university lab, you look up into the night sky and you see this 73 billion-ton sphere of rock just sitting there in a vacuum.
Exactly. You are treating the entire moon as one giant Weber bar.
That is just...
It's mind-blowing.
It is the elegant core of the proposition. When a dasahertz gravitational wave washes over the Earth-Moon system, it doesn't just pass harmlessly through.
It grabs the moon.
It interacts with the mass of the moon, yes.
Mm-hmm.
It induces a global structural deformation. The entire celestial body is forced to minimally stretch and compress.
I am really trying to visualize the sheer scale of that. You have a wave originating from this cataclysmic collision of black holes millions of light years away.
Right.
It travels across the endless void, arrives in our solar system, and then rings a 2,000-mile wide rock like a cosmic tuning fork. That's exactly it. And because of the moon's immense size and its specific material properties, like its sheer modulus, its density, its natural resonant frequencies, happen to align beautifully with the dc-hertz gravitational wave band.
No way. It just naturally lines up.
It does. It is naturally tuned to the exact missing octave we're looking for.
But wait, I have to challenge the mechanics here for a second.
Please do.
I understand how a solid, precision-machined aluminum cylinder rings in a lab. Aluminum is uniform, right?
Yeah.
The atoms are locked in a nice, neat metallic lattice.
Clear.
The moon is definitely not a precision-machined object. It is a battered, dusty, fractured orb of silicate rock. I mean, it has been pummeled by asteroids for 4 billion years.
It absolutely has.
So how can a shattered rock ring like a bell? Wouldn't all the cracks and craters and dust just absorb the energy and deaden the vibration completely?
You have just hit on the exact contradiction that stalled this entire field of research for decades.
Really? So physicists thought of this before.
Oh, the idea had been around. But to figure out if the moon could effectively act as an antenna, early theoretical physicists had to build mathematical models of its interior.
Okay, to run simulations.
Right. But the equations required to model a global seismic response to a gravitational wave are notoriously difficult.
Because there's so much data.
Because of the complexity. So I'm guessing you can figure out what they did.
In physics, whenever the math gets too messy, they usually just take a shortcut, right? They assume the object is a perfect frictionless sphere in a vacuum.
That is essentially exactly what happened. They relied on what we call ideal lunar models.
Ideal models.
Because in the absence of high-resolution computational power back then, the only way to solve the equations was to assume the moon was structurally isotropic and radially symmetric.
Meaning they modeled it as a perfectly smooth, evenly layered, homogeneous ball.
Yes, a perfect sphere.
Which is about as far from the reality of the moon as you can possibly get. I mean, anyone with a cheap backyard telescope can see it's not smooth.
It is remarkably rugged. But honestly, more importantly than the visible craters you can see, those early ideal models completely ignored the geological reality of the lunar crust.
The actual rock layer.
Right. Because the moon has incredibly strong lateral heterogeneity.
Okay, let's break down strong lateral heterogeneity. I know lateral basically means side to side, and heterogeneity means varied or diverse.
Right, so it means that as you move horizontally across the moon's surface, the structure beneath your feet changes dramatically.
Okay, that makes sense.
Well,
Earth has that too, right?
Very much so. On Earth, an oceanic crust is very, very different from a continental crust.
Right.
And on the moon, you have these vast impact basins where the crust is incredibly thin, and they're surrounded by mountainous highland regions where the crust is heavily fractured and incredibly thick.
So it's totally uneven.
Totally uneven. And you also have a layer called the megaregolith.
The megaregolith, that sounds intense.
It's a deep zone of just shattered, pulverized rock caused by eons of meteor impacts.
So the whole surface is just covered in a thick layer of cosmic rubble.
Basically, yes. So applying an analogy here, the theoretical physicists modeled a pristine crystal wine glass that would ring with a pure, sustained note.
Right, the perfect sphere.
But the geophysicists looked at it and said, no. The moon is a thick, chipped ceramic coffee mug, and it's covered in a thick layer of shattered gravel.
That is a great analogy, the chipped coffee mug.
And the assumption, much like your intuition a moment ago, was that the shattered gravel of the megaregolith and the uneven thickness of the crust would cause massive attenuation.
Attenuation, meaning the dampening of a wave.
Exactly. When a seismic wave hits a fracture or a major change in material density, some of the energy naturally scatters. It diffuses into the surrounding material.
Because it's hitting a boundary.
Right. So the logical assumption for years was that the moon's rugged, messy reality would ruin its ability to sustain a clean resonance from a tiny gravitational wave.
Okay, but if the geology ruins the resonance, how does this idea even survive to the present day?
It survives because geophysicists decided to stop guessing and actually start modeling the chaos.
Oh, they built a better model.
Yes. They aren't afraid of messy geology. They actually have the computational tools to simulate seismic wave propagation through highly irregular media.
But that sounds like a computational nightmare. I mean, if you aren't using a smooth sphere, you have to map every major density change, every thick spot, every thin spot in the crust.
It absolutely requires immense computing power. And crucially, it requires an understanding of numerical artifacts.
What are numerical artifacts?
So when you run simulations on a grid in a computer, if the grid resolution is too coarse, or if you try to push high-frequency waves through a jagged digital model, the simulation will glitch.
Like a video game glitching out.
Exactly like that. It creates false signals or artificial dampening that don't actually exist in reality. It's just a math error.
Oh, wow.
But the new teams knew how to build a high-resolution numerical model that integrated the actual topography and crustal thickness of the moon without breaking the math.
So they threw out the perfect crystal wine glass model entirely.
Talked it out.
And they painstakingly built a digital version of the real battered lumpy moon.
Yes.
And then they simulated what happens when a 2 Hertz gravitational wave hits it.
They did.
Well, given all that shattered rock we just talked about, I'm expecting the signal to just die instantly.
See, here is where the physics gets so counterintuitive and, frankly, absolutely thrilling.
Really?
When they ran the high-resolution numerical models, the signal didn't die at all.
It didn't.
The messiness didn't ruin the resonance. It amplified it.
Wait, what?
Yes.
The flaws, the varying thickness, the rough topography made the signal stronger. How is that physically possible? We just said fractures and variations scatter energy.
They do scatter energy, but they also trap and reflect it.
Okay, I'm going to need you to explain that.
What they discovered is that the moon's uneven crust creates a massive impedance contrast.
Acoustic impedance, like how sound behaves differently when it moves from air into water.
Exactly. The rocky outermost layer of the moon, the crust, has a significantly lower density and a lower seismic velocity than the dense mantle deep beneath it.
Okay, so there's a hard boundary between the crust and the mantle.
Right. So when a wave traveling through the deeper, denser moon hits the boundary of that lighter crust, a large portion of the wave's energy actually reflects back.
It bounces.
It bounces. And if the crust is exceptionally thick in a certain region, it acts as a local waveguide.
A waveguide, like a tunnel.
More like a resonant chamber. It's a chamber that traps the seismic energy bouncing around inside it.
Oh, I see. So instead of the vibration bleeding away, it gets bottlenecked in these thick regions of the crust, just bouncing back and forth off the boundaries.
That is exactly the mechanism. Overall, across the entire lunar surface, they found that regions with a thicker crust amplified the gravitational wave signals by up to 10% compared to the old ideal sphere models.
10%. I mean, that is huge, especially when we are hunting for something this incredibly faint.
It is significant.
But the models highlighted something even more extreme than 10%, didn't they? I remember reading there is a specific frequency where the crust doesn't just give a 10% boost, it goes completely hyperactive.
Yes, you're referring to the 0.1 hertz sweet spot.
The sweet spot.
There's simulations which ran from 0 up to 0.2 hertz revealed something extraordinary at exactly 0.1 hertz.
Which is right in the dead center of our blind spot.
Exactly. At that frequency in specific thick crust locations, the localized amplification wasn't 10%.
What was it?
The signal was boosted by more than a factor of 10.
Wait, 10 times the amplitude? A 1,000% increase in the signal strength simply because the crust is lumpy.
Yes. The localized ruggedness provides an acoustic boost that completely changes the feasibility of detection.
That is just, it's staggering.
It is. And to verify that this wasn't just some glitch in the numerical model, they validated the findings using semi-analytical models involving harmonic decomposition.
Okay, harmonic decomposition is a heavy, heavy phrase. Let's translate that for someone who hasn't taken advanced wave mechanics.
Of course. Think of a drum head.
Like a snare drum.
Sure, a snare drum. If you strike a drum right in the dead center, the skin vibrates up and down in a simple, uniform bowl shape.
Right.
That is the fundamental mode. But if you hit the drum off-center, or with a strange-shaped mallet, the skin ripples in complex, overlapping patterns.
Right, it kind of wobbles.
Yes. Some parts go up, while other parts go down, and they're separated by nodal lines that don't move at all. Those complex patterns are higher-order harmonics.
Okay, so harmonic decomposition is the mathematical process of looking at that chaotic, rippling drum head and separating out all the individual simple patterns that are overlapping to create the mess.
Precisely. You deconstruct the mess into simple parts. Now replace the 2D drum head with a 3D sphere, which is the moon.
Okay, I'm with you.
When a gravitational wave strikes it, the moon vibrates in a superposition of many different spherical harmonic modes.
Lots of overlapping wobbles.
Right. Now, if the moon were a perfect sphere, these different modes would largely ignore each other. They would vibrate independently.
Because there's no structure to force them to interact. It's just smooth.
Exactly. But because the real moon is laterally heterogeneous, because the crust changes thickness drastically from point A to point B, the spherical symmetry is broken.
The perfect shape is ruined.
That's right. And this broken symmetry causes the different harmonic modes to actually couple together.
They crash into each other.
The rippling patterns crash into the thick crust and overlap. And in certain regions, specifically at that 0.1 hertz frequency, the overlapping modes constructively interfere.
Constructive interference. Okay, it's like when two ocean waves happen to meet at exactly the right moment, peak to peak.
Yes.
And they combine to create a rogue wave that is twice as high. The varying crust is forcing the seismic vibrations of the moon to pile up on top of each other, creating these massive localized spikes in the signal.
That is exactly what is happening. The physical imperfections of the moon, those thick highland crusts, those deep basins, they act as an elaborate acoustic lens.
An acoustic lens. Wow.
They focus and compound the seismic energy generated by the stretching of spacetime.
That is just a spectacular irony. I mean, think about it. The very thing that physicists assumed would destroy the signal, the chaotic, messy reality of nature, is actually the only reason the signal might be loud enough for us to ever detect it.
It really is beautifully ironic.
If the moon actually was the pristine mathematical sphere they originally modeled, this idea would be dead in the water.
Completely dead. It is a very humbling reminder that our simplified models are really only scaffolds. Reality is always more complex, and sometimes that complexity is highly advantageous.
We just have to look closer.
Exactly. But it's also really worth noting that this breakthrough didn't happen purely because computers got faster.
Oh, it didn't?
No, it happened because of a human element. It required a collision of disciplines that very rarely speak to each other.
Oh, the interdisciplinary angle. That origin story here is fascinating, especially because of how disconnected modern science has become.
It really is siloed.
You have planetary geologists who spend their entire lives just debating the mineral composition of lunar dust.
Right.
And on the other end of the campus, you have astrophysicists calculating the orbital decay of black holes. I mean, they speak entirely different jargons, they attend different conferences, they publish in completely different journals.
They might as well be speaking different languages.
So how did they bridge that gap here? How did this even start?
Well, it began with a surprisingly straightforward inquiry. An astrophysicist was looking into the feasibility of designing a LIGO-like system on the moon.
Okay, so essentially building a traditional laser interferometer, but just placing it in the vacuum and low-gravity environment of the lunar surface.
Right, which is a very valid idea on its own.
If Earth is too noisy, just build the machine on the silent moon.
Exactly. But to build a machine of that incredible sensitivity anywhere, you must intimately understand the local seismic background.
You have to know how much the ground naturally shakes.
You have to know what kind of micro vibrations the ground is naturally producing so you can engineer the right shock absorbers. So the astronomy side reached out to the geophysics side, specifically asking an expert on deploying lunar seismometers.
It was basically just an engineering consultation. Like, hey, we want to put lasers on the moon. How much does the ground shake?
Essentially, yes.
Yeah.
But from that single pragmatic question, the seismology expert realized they were dealing with something much bigger.
They saw the potential.
He became drawn into this incredible multidisciplinary pursuit. He brought his deep geophysics background to the table. Then planetary scientists provided the topographic and crustal thickness maps.
And the astrophysicists brought the gravity waves.
Right. The astrophysicists brought the theoretical physics of gravitational waves and the harmonic decomposition math.
I just really respect that because it highlights a massive flaw in how we usually do science today. We really incentivize hyperspecialization.
We do.
A researcher is heavily rewarded for knowing absolutely everything about one incredibly narrow subfield. But the grandest mysteries of the universe, like turning a planetoid into a gravity wave antenna, they don't care about our academic department boundaries.
Nature does not operate in silos. The interactions are fundamentally holistic.
Right. The universe is all one thing.
So, the geophysicists had to learn the frontiers of astronomy, and the physicists had to accept the rugged, messy reality of lunar dirt. They had to forge a shared vocabulary just to talk to each other.
And what emerged from that friction was a completely novel approach. Instead of building an instrument on the moon,
They realized they could use the moon as the instrument.
it's brilliant, truly. But okay, let me put my skeptic's hat on for just a moment here.
Go right ahead.
This is all still theoretical, right? I mean,
Right.
we have incredibly complex computer models running harmonic decompositions, and they're simulating gravitational waves hitting digital rock on a screen. But at the end of the day, it's just math on a screen. How do we transition this from a fascinating theory into actual hard science? Because we can't just simulate it forever.
You are echoing the core tenet of the scientific method there.
Well, thank you.
A model, no matter how elegant or high resolution it is merely a hypothesis until it is empirically verified by reality.
So we have to go there.
And that is exactly where this project is heading. We are going back to the moon to test the ground truth.
Okay, let's talk about the timeline and the hardware then. What is the actual proving ground for this theory?
The proving ground is China's Change 7 mission, which is currently slated to launch in the fall of 2026.
2026, that's very soon.
It is. This is a highly ambitious mission targeting the lunar South Pole. And among its massive payload of scientific instruments, it will carry a state-of-the-art broadband lunar seismometer.
Now, obviously, we've put seismometers on the moon before, right? The Apollo astronauts deployed several of them back in the day.
Yes. The Apollo passive seismic experiment was revolutionary. It operated from 1969 until 1977.
And it taught us a lot, didn't it?
It fundamentally changed our understanding of the moon. It proved the moon was seismically active, recording thousands of moonquakes.
Right.
It even gave us our first rudimentary understanding of the lunar interior, finally confirming the existence of a crust, a mantle, and a small core.
I actually remember reading that when they crashed part of an Apollo rocket into the moon, the seismometers recorded it ringing like a bell for over an hour.
They did.
Which honestly just reinforces the whole Weber bar concept we were just talking about.
It absolutely does. And it rings like a bell for so long because, unlike Earth, the moon is bone dry.
Oh, water stops the ringing.
Yes. Water on Earth acts as a massive dampener for seismic waves. It lubricates the rock and absorbs energy.
Makes sense.
But the dry, fractured lunar rock allows seismic waves to bounce around for a very long time without losing energy.
Wow.
However, the Apollo network had major limitations.
I assume the tech was just old.
The tech was cutting edge for the 1970s, but they lacked the broad frequency response and sensitivity of modern geophones. Plus, they were all clustered near the equator.
And we turned them off in 1977. So we've basically had a nearly 50-year gap where humanity hasn't listened to a single vibration on the moon.
Exactly. We've been deaf to the moon for half a century. But Chang'e 7 will end that drought. And the primary investigator for this new broadband seismometer is actually one of the key geophysicists from the gravitational wave study.
Oh, that is perfect synergy. Okay, so we land at the South Pole, we deploy this incredibly advanced broadband seismometer into the lunar dust, and we start waiting for a 0.1 hertz signal from a black hole merger to rattle the moon.
Okay, let me stop you right there, because we really need to manage expectations and understand the iterative nature of this kind of science.
Uh-oh. What's the catch?
The seismometer aboard Chang'e 7 is not going to detect a gravitational wave.
It's not.
No. It fundamentally lacks the extreme sensitivity required to measure a spacetime-induced perturbation.
Hang on. I need to push back hard on this.
I figured you would.
Because if the entire point of this incredible multidisciplinary breakthrough is to use the moon as an antenna for gravitational waves,
right,
and you're launching a mission to the South Pole in 2026, led by the guy who co-authored the paper.
Yes.
Why are you sending an instrument that can't hear the signal? Space missions cost billions of dollars. Why not just wait and build an instrument that actually does the job?
It's a completely fair question, and it really speaks to how the public often perceives scientific progress versus the painstaking, slow reality of how it actually has to happen.
I mean, it just seems like a wasted trip.
I understand that.
Yeah.
But you cannot simply drop an ultra-sensitive gravitational wave detector onto an alien landscape without first characterizing the environment.
Why not? If it's hypersensitive, it'll just pick up everything.
That's precisely the problem. It will pick up everything.
Oh.
Remember why we left Earth in the first place.
Because Earth is too noisy.
Right. The moon is much quieter than Earth, but it is absolutely not silent. It is a continuous, complex, seismic background chatter all its own.
But what's causing the chatter? There are no oceans crashing, there's no wind, no tectonic plates dragging around.
There are three primary sources of noise on the moon that we have to account for.
Okay, what's its first one?
First, you have thermal moonquakes.
Thermal, like from heat?
Yes. The moon lacks a significant atmosphere to distribute heat, so the temperature swings are extremely violent.
How violent?
Over a single lunar day-night cycle, the surface transitions from 250 degrees Fahrenheit during the day down to negative 200 degrees at night.
Good grief. That is a massive swing.
It is. And that intense thermal expansion and contraction causes the crustal rock to constantly crack and pop.
Okay, like the creaking of a house settling at night, but on a planetary scale.
Exactly like that. It's a constant popping noise seismically.
Okay, so that's thermal. What's the second source?
Second, you have deep moonquakes. These are driven by tidal stresses.
Tidal stresses from Earth.
Yes. Even though the moon is tightly locked to Earth, meaning it always shows us the same face, its orbit is actually elliptical. It's an oval.
Right.
So as it moves closer and further away from us in its orbit, Earth's massive gravity subtly stretches and relaxes the moon.
Like kneading dough.
Yes, and that causes deep structural friction and deep quakes inside the moon.
Okay, so we've got surface cracking from heat and deep rumbling from Earth's gravity. What's the third?
Finally, you have the constant barrage of micrometeorites hitting the surface. Without an atmosphere to burn them up, they just slam right into the rock continuously.
So the moon is literally humming, cracking, and getting pelted with rocks constantly.
Yes, it is a noisy place, just a different kind of noise than Earth.
Okay, I'm starting to see the problem.
Right. If you deploy a multi-billion-dollar ultra-sensitive gravitational wave detector without deeply understanding that background noise first, you will just get a chaotic mess of data.
It would just be static.
You wouldn't be able to distinguish a localized thermal pop in the rock from the majestic 0.1 hertz ringing of a cosmic event.
Because they'd all just blur together.
Exactly. So Change 7's role is absolutely vital. It is a calibration mission. It is going to the South Pole to measure the exact acoustic profile of the lunar room.
Okay, I see the logic now. Before we can isolate the 10-fold amplified cosmic whisper, we really have to know exactly what the room's air conditioner sounds like.
That is a perfect way to phrase it. We have to record the baseline hum of the moon itself.
And then what do they do with that baseline hum?
The goal is to take the actual background noise data recorded by Change 7 and feed it back into their high-resolution digital models.
Ah, to update the model.
Right. They will theoretically simulate the output of the seismometer based on their messy, thick crust digital models, and then compare that to the empirical ground truth it just recorded.
And if the real data matches their simulation,
then they know they've successfully built a true mathematical twin of the moon.
That is incredible. And once that digital twin is verified, what happens next?
Once it's verified, it becomes a definitive treasure map.
A treasure map.
It will tell us exactly how the noise behaves, and more importantly, it will allow us to map the precise coordinates of the thick crust regions that offer the greatest gravitational wave amplification.
It tells you exactly where to put the microphone.
Yes, it dictates exactly where future missions should land to maximize the science payback.
So it's a stepping stone. You measure the noise in 2026, so you know exactly where to drop the real deal, ultra-sensitive payload in maybe 2036.
Exactly. It is the only rigorous, scientific way to turn a naturally occurring celestial body into a finely tuned astronomical observatory. You have to do the groundwork.
Wow. When you step back and look at the whole picture, the sheer audacity of this plan is just breathtaking.
It really is a testament to human ingenuity.
I mean, we started with a fundamental limitation of our own world, right? The Earth is simply too loud and restless to let us hear the Decider's band.
The missing middle register of the cosmic symphony.
Right, and that limitation forced researchers to look outward, adapting the legacy of Joseph Weber's solid-state resonant bars from the 60s to the most massive object within our reach.
The moon itself.
But the breakthrough only happened because they refused to rely on the clean, easy math of a perfect sphere.
Which is so often the trap in theoretical physics.
By dragging geophysicists into the astrophysics lab, they confronted the jagged, laterally heterogeneous reality of the moon's crust.
They embraced the messiness. And in doing so, they unlocked an acoustic miracle.
The rugged flaws of the lunar crust don't dampen the signal at all.
No, they act as a massive resonant chamber, trapping and amplifying the very waves we are desperate to hear by a factor of 10.
It's an amazing journey, from a blind spot in our telescopes to a cross-disciplinary revelation leading directly to the South Pole of the moon in 2026 to basically measure the silence before the symphony begins.
It really does make you rethink how you view the night sky, doesn't it?
It absolutely does. The next time you are standing outside, looking up at that silver cratered rock, realize that you aren't just looking at a dead world.
No, you are looking at a giant cosmic antenna, just waiting to be tuned to the deepest frequencies of the universe.
It completely challenges us to reconsider the utility of everything in our solar system. The moon is no longer just a destination to plant a flag on. It is a lens through which we will eventually view the rest of the cosmos.
A literal telescope made of rock.
Which leaves me with a final thought to chew on for everyone listening.
Oh, I like these.
The only reason the moon can serve as this incredible diagnostic tool is because of its immense imperfections.
Right, the craters, the thick crust.
The very fractures, the uneven thickness, the chaotic history of getting smashed by rocks, the things that physicists initially thought would ruin it completely.
The flaws?
Yeah. If the physical flaws of our nearest neighbor are the exact mechanisms required to unlock the deepest secrets of black holes and the early universe, What other messy, chaotic, or, flawed systems here on Earth or even in the structures of our own lives aren't actually broken at all?
That is a fascinating perspective.
Maybe they are just perfectly designed solutions waiting for us to find the right frequency.